Yes, sir. Okay, sir. Deflections. So this is one of the most important topic from the GATE point of view, and definitely you will expect a question from this topic. So here the students will have some of the students face difficulty while studying this topic. Okay, so very good evening, Krishnamurthy. So here in deflections, the methods available for solving are Macaulay's method. So let me just give you the introduction, then I will take you to the main part. Macaulay's method. Next is movement area method. Movement area method. Next is conjugate beam method. Next is strain energy approach. Strain energy approach. So here Macaulay method, basically it involves with mathematical computation, and movement area method and conjugate beam method are the graphical methods. These two are the graphical methods. Right. Now, here we need to select which method is suitable, which method is suitable, or which method can save your time. Which method is suitable or which method can save your time. Okay. So most of the problems of the cantilever beam, can be done by using simply movement area method. Okay, so most of the problems of the cantilever beam, whether it is carrying uniformly distributed load or whether it is carrying uniformly varying load, or it is a combination of point loads or couples, still movement area method can be recommended. Okay, but in our examination point of view, if you see the problem, so either they might give you a completely, like in a cantilever beam, is if it is loaded, so that loading will be either a uniformly distributed load, either it will be a uniformly varying load. So this question was there in the 2018 or 19 or 20 paper, 2019 paper, I believe. So, and either a point load and couple. So the concentrated point load and couple, they are giving two in combination, but with the uniformly distributed load, and uniformly varying load, they are giving only one loading situation. Point load or couple is not added here into these for these two situations. Point load and couple is not added. They are giving only one loading situation. So even if point load is added or a couple is added, still we can do the problem. If we are using the Morse movement area method or Morse method. Okay. Now, the governing equation for the deflection is EI times of d square y by dx square equal to m, or moment about a section xx. We write it. Okay, so we write it as EI into d square y by dx square equal to mx. So now if I integrate this equation, EI in dy by dx equal to 1 by EI times of integral mx dx. This term is what? This term is what? It is the area of BMD diagram. This is the integral m dx is the area of BMD diagram. Okay. This term is area of bending moment diagram, BM diagram. So for simple areas like rectangle, triangle, or parabolic areas, we can do the computation. Okay. And upon double integrating this term, that is y is equal to EI 1 by EI times of double integral mx dx. And this term here, it will be, this term here, it will be written as movement of area. Movement of area under bending moment curve, BM curve, movement of area under BM curve, or this slope we can write it as theta is equal to, this is area divided by EI. And for deflection, this will be the formula for slope, and for deflection, we can write y is equal to a into area into x bar. X bar is the centroidal coordinate. X bar is the centroidal coordinate divided by EI. So this is what we can write. This is what we can write. Okay, for Morse area method, for Morse method or moment area method. So for cantilever beam, so I will recommend to use this method. Okay. So here the integration, please understand the word if you are writing integral mx dx, which indicates the area, and if you are doing the double integration, which means that you are searching for, you are taking the movement of that area. Okay. So I will come to the Macaulay's method also. Okay, so let us take this question. Let us take this question. Two identical cantilever beams are supported as shown with their free ends in contact through a rigid roller. After the load P is applied, the free ends will have. After the load P is applied, the free ends will have. Now, let me just draw the free body diagram for this. So let us say this is cantilever A and this is cantilever B. So for A, these two are joined together by a rigid roller. So if I say that deflection of cantilever beam A and beam B, if both are same, then the beams will be held in contact. Okay. So if the deflections are not same, then there will be no contact between the beams. If the deflection is not the same, then there will be no contact in the beams. So let me just draw the free body diagram. This load P, it may be acting at the mid span or maybe at two-thirds of the span. So wherever it is, that is not a question. So when the P is going to act here, there will be a normal reaction at the roller. Let us name it as R. Okay. Let us name it as R. Next, similarly for beam B, this is cantilever beam A, cantilever beam A. Similarly for beam B, you will have the same reaction R downwards. You will have the same reaction downwards. Now, here, if these two beams are required to be in contact, if these two beams are required to be in contact, then both should have the same deflection. Both should have. So here we are, it is compulsory for us to maintain the contact. It is compulsory for us to maintain the contact. So both should have same deflection. Both should have same deflection. Okay. Now, if you compare the cantilever beam A and cantilever beam B, the loading condition of both the beams is different. If you compare cantilever beam A and cantilever beam B, the loading condition for both the beams is different. So when it is different, when it is different, here you will they might have the equal slope, they might have the same deflection. Okay, they might have, or they, if you are saying that there has to be contact between the beam A and beam B, so both should have the same deflection. Okay, both should have same deflection. The second point is that due to the variation in loading condition, due to the variation in the loading pattern, due to the variation in the loading pattern, both will have different slope. Both will have different slopes. Both will have different slopes. So that is option A says that equal deflections but not equal slopes. Option A says that it has having equal slopes, sorry, equal deflections but not equal slopes, but not equal slopes, right? So this is one question where some logical reasoning you have seen here, right? Now let us go to another question. Let us go to another question. In the propped cantilever beam carrying a uniformly distributed load. Okay, this is the cantilever beam. Okay, it is carrying a uniformly distributed load. The reaction at support B, yes, this is the support provided here. The reaction of this is how much? The reaction of this support B is how much? This is called as prop. This is called as prop. Yes, Guru Vignesh, I will definitely take your query. So today, just let me focus on the movement area method. I will discuss the strain energy approach also. I will discuss good number of problems in strain energy also. Okay. So now if you want to, one way is to by heart the formula, or other way is to, you can derive the formula. One way is to by heart the formula, another way is to derive the formula. Okay. So now what I can do is I will give you some standard, I'll share some simple principles here. Okay. So if the beam bending moment diagram, here we have seen bending moment diagram, if it is like this or triangle, right? So here let us say this is height h and b. So area of this, you know this already, that is half bh, and centroid, that is from this side, or from this side if you are measuring the centroid, it is going to be 2/3 of base, 2/3 of base, right? For rectangle, you know this already, area of this rectangle will be b times of h, and centroid will be at b by 2. These are well-known relations. Okay. Right. And next is Now, if you have the spandrel, if you have the spandrel, okay, if you have a spandrel like this, or the equation of this spandrel will be y is equal to kx power n. Y is equal to kx power n. This is the equation of this spandrel. Okay. Now, area of this spandrel will be, say this is base and say this is height. So area of this will be equal to 1 by n plus 1 times of BH. This will be the area. This will be the area. Okay, please remember that. Here you will have a line of the form y is equal to x. Here you will have a line of the form y equal to x, but here it is y is equal to kx power n, kx power n. So here it is x power 1, x power 1. So I here, if I write in place of n equal to 1, I will get the area of triangle. I will get the area of triangle. Similarly, here for centroid, I have written centroid as 2/3 of base. Here I will write the centroid as n plus 1 by n plus 2 into base. N plus 1 by n plus 2 into base. And from here, if I am approaching from the right angle edge, if I'm approaching from the right angle edge, it will be b by 3. If I am approaching from right angle edge, it will be b by 3, or 1/3 of base. 1/3 of base. So please remember this formula, then it would be much easier whether you are solving for uniformly distributed load or whether you are solving for, yes, Guru Vignesh, I will discuss that also. How to solve UVL cantilever. Yes, we will see that too also. Guru Vignesh, need not to worry. Just remember this formula. Just remember this formula. If you remember this formula, then you can solve the problem with UDL as well as UVL also. So this will be 2/3 of base. Sorry, not 2/3. For triangle, it is going to be 2/3. For triangle, it is going to be 2/3. And here it is n plus 1 by n plus 2 times of base. N plus 1 by n plus 2 times of base. And this will be the other side. From the right angle edge, if you are approaching, this value will be 1 by n plus 2 times of base. 1 by n plus 2 times of base here. So this is spandrel. Now, if the equation of the curve, is y is equal to kx power n, this is called as spandrel. This is called as spandrel. You may have a parabolic spandrel or cubic parabolic spandrel, whatever it is. Okay, so n, I am taking n as a general condition. But if you have an equation like this, y is equal to k1 x power n minus k2 x power n minus 1 plus k3 x power n minus 2. So this is not a spandrel. This is not a spandrel. I cannot use, if my bending moment equation should be in the form of y is equal to kx power n. My bending moment equation should be of the form y is equal to kx power n. So this will be not spandrel. I cannot apply these formulas if the equation is changing to this form. So not a spandrel. These formulas are invalid for this situation. It is invalid. Okay, I cannot apply this. Please do remember. Not applicable. Okay, please remember, only for this I can apply. These two formulas are applicable for this equation. If you have an equation or bending moment at section XX, if it is following this pattern, that is bending moment at section XX, let us say you have got it as 2x square, then you can use this formula. If you have an equation like this, a moment about section XX as 2x square minus or plus 10x. If it is like this, then I'm sorry to say we cannot use these formulas. We cannot use these formulas. We have to search for some other alternative. Okay. So let me just do this problem. Let us go to this problem. So here I need to split this beam, that is beam with uniformly distributed load, beam with uniformly distributed load, and this reaction is equal to point load. Cantilever beam with a point load here. Cantilever beam with a point load here. Right. So this is W and this is L. Now let me just write the moment about section XX. Take here, draw the section XX here. Draw the section XX here. This is X length. So what will be movement at section XX? It is W into X by 2. W into X by 2. W into X by 2, which is W by 2 times of X square. This is of the form Y is equal to Kx power N. Y is equal to Kx power N. Okay, this is of the form Y is equal to Kx power N. There is no additional term present here. There is no additional term present here. Right. So area of this will be equal to, area is equal to, let me do one thing. Let me just draw the BM diagram for this. The bending moment at the free end will be 0, and at the fixed end, this bending moment will be W into L by 2, which is WL square by 2, which is WL square by 2. This will be definitely a second degree curve or X power 2 behavior. This will be a second degree curve or X power 2 behavior only. This will be length L. Area of this curve is how much? That is 1 by n plus 1, 1 by n plus 1 times of BH. What is n here? 1 by n is 2 here. 1 by 2 plus 1 into base is length here, and height is WL square by 2. So this is equal to, area will be WL cube by 6. WL cube by 6. This will be the area. This will be the area. Right. Now, so next is the centroidal coordinate. Centroidal coordinate. Now remember here, in the cantilever beam, this X bar, what you're going to measure in cantilever beam, the X bar as per this formula, that is as per the deflection formula, the X bar where you are going to measure always from the free end, not from the fixed end. You are going to take the X bar from the free end, not from the fixed end. Please do remember that. You are going to measure the X bar from the free end only. So here X bar will be equal to n plus 1 by n plus 2 times of base, which is equal to 2 plus 1 by 2 plus 2 times of base. Here it is L. So that is 3 by 4 times of L. That is 3 by 4 times of L. Now, deflection here will be equal to AX bar by EI. So area we have computed as WL square or WL cube by 6. Area we have computed as WL cube by 6 into WL cube by 6 into X bar is 3 by 4 times of L divided by EI. So this is equal to WL power 4 divided by 8 EI. This is the standard result. You can remember this or you can derive it. Right. Now, Similarly, I did not consider here the prop B. I did not consider here the prop B. Now I am going to consider that. Now I am going to consider that. Okay, there is a prop at B, location B. Let me write that reaction as, yes, Yosing, what is your question? I will reply to your question, boss. Hi, Yosing. So now the bending moment diagram for this, will be moment about section XX. If you take, we are aware of this, very much aware of this. Bending moment diagram for this, it will be a simple triangle, okay, of length L, and this will be RB times of L. This will be the bending moment, RB times of L, and area for this is equal to, half into base is L, and height is RB times of L. Height is RB times of L. Hi, Venkatesh. So this is equal to RB L square by 2. And centroid, that is x bar, that here, centroid here will be equal to, that is 2/3 of L. X bar will be equal to 2/3 of L. 2/3 of L. Right. So deflection here, deflection will be equal to AX bar times of EI. So area is RB L square by 2 into 2/3 of L divided by EI. So this will be RB into L cube by 3 EI. That is WL cube by 3 EI, which is also a standard result. Venkatesh, if you are approaching from apex, this is called as apex. If you are approaching from apex, your X bar is going to be 2/3 of L. And if you are approaching from right angle edge, it is 1/3 of length. Okay, it is 1/3 of length. Please remember this, Venkatesh. Okay, so now the deflection at B, this is the deflection at B, and this is also deflection at B. Equate these two. This is your equation number 1, and this is your equation number 2. So 1 is equal to 2. If I take it, I will get it as WL power 4 by 8 EI is equal to RB into L cube divided by 3 EI. RB into L cube divided by 3 EI. So here RB will be equal to, that is 3 times of WL by 8. This is the reaction at the prop. Okay. Sir, how to draw the BMD diagram for this? Guru Vignesh, for which one you are asking? For point load, you are asking? Because this is a simple calculation for the point load. Bending moment at fixed end, it will be maximum here. This is a simple point loading case. Okay. So in case if you are not able to remember this formula, how you can derive by using moment area method, I am telling that. Or else let us say that, take the moment at section XX, Vignesh. What is the moment at section XX? That is RB times of X. At X equal, this is X equal to 0 location, and this is X equal to L location. At X equal to 0, you will have 0 bending moment. At X equal to L, you will have RB times of L. Sir, how to draw the bending moment diagram for the propped cantilever? Okay, you want me to draw? Okay, just a minute. I will discuss that also. For the propped cantilever. Okay, fine. I'll take that. This is the propped cantilever given to you. This is the reaction. You have estimated the value of reaction also. So what you can do is here, this is A, this is B. Now RA plus RB, that is RA plus RB equal to WL. This is the equilibrium equation, that is sigma Fy equal to 0 I am writing. And RB we have calculated that as 3WL by 8. 3WL by 8. And RA comes out to be as WL minus 3WL by 8, which is equal to 5WL by 8, which is equal to 5WL by 8. That is RA. Now moments about A you take it. Moments about A you take it. So moments about A, if I'm taking, there is a fixing moment, that is minus MA plus W into L by 2, that is WL square by 2, and minus RB. This is minus MA in anti-clockwise. About A, this is acting in clockwise, and RB is also in anti-clockwise. Minus RB. RB is how much? 3WL by 8 times of L. This is equal to 0. This is equal to 0. So MA is equal to how much here? WL square by 2 minus 3WL square by 8. So you will get some value here. You'll get some value here. So here the moment will be at A, and it will be anti-clockwise sense. At A, it will be anti-clockwise sense. Okay. So 1 by 2 minus 3 by 8. 3 by 8 means that is equal to 1 by 8 times of our WL square by 8. So this will be WL square by 8, and the what do you call, the variation is going to cross the 0 line. Okay, somewhere here you will get bending moment equal to 0. In propped cantilever, you will definitely get a point of contraflexion. Okay, somewhere here I will be getting that as 0. What you can do here is you can take the section XX, that is RB times of X minus WX square by 2 equal to 0. What is RB here? 3 by 8 times of WL into X minus WX square by 2 equal to 0. So solve this, you will get the location where bending moment is changing the sign. This is given as UDL. This will be second degree curve or X power 2 behavior. Right, let us go to next problem. So this was the discussion of, here I am trying to discuss the concept of calculating the deflection. If it is a propped cantilever, how that we can calculate the reactions. If it is a propped cantilever, how that we can calculate the reactions. And for the same propped cantilever, what is the bending moment at the fixed end? Okay, what is the bending moment at the fixed end? It will be definitely less than WL square by 2. It will be definitely less than WL square by 2, which you have got it for without the prop. Okay. Or else you can use the Macaulay's method to do this problem. Right. So let us go for next problem. A simply supported beam carrying a concentrated load. Okay, a simply supported beam carrying a concentrated load at the midspan, that is W at the midspan is there. This is L by 2. This is L by 2. Okay. Next is deflects by delta 1. So this is undergoing deflection of delta 1, right? And there is another beam, the same beam is there, which carries uniformly distributed load and deflects by delta 2 amount. Deflects by delta 2 amount. Okay, deflects by delta 2 amount. This is uniformly distributed load, W. Okay. Now, this here, what I suggest is you to remember the standard result. What I suggest you is to remember the standard results. Okay. Or else, as suggested by that Guru Vignesh, I think somebody has rose to discuss the strain energy approach also. Guru Vignesh, we can solve this by strain energy method also. Okay, both are symmetrical loading conditions. Both are symmetrical loading conditions. We can solve that by that is by strain energy method also, or you can remember this result as, that is, for this the result will be delta will be WL cube by 48 EI. WL cube by 48 EI. Okay, and next delta here will be 5 WL power 4 by 384 EI. Next will be this. You can remember these two as a results and then directly you can calculate. Okay. So here delta 1, that is delta 1 by delta 2, that is ratio of delta 1 by delta 2, simply supported beam carrying concentrated load W at the midspan deflects by delta under the load. If the same beam carries W such that it is distributed uniformly over entire length and goes by the deflection of delta 2 at the midspan, then the ratio of delta 1 by delta 2. So ratio of delta 1 by delta 2 is, so delta 1 is WL cube by 48 EI, and this we can write it as 5 into small w into small w into L in times of L power 3 divided by 384 EI, divided by 384 EI, divided by 384 EI. So this we can write it as 5 WL cube by 384 EI, 384 EI. So this I can write it as 5 W, that is delta 2, that is delta 1 by delta 2. Right, that is 5 WL cube by 384 EI. So this WL cube will be cancelled here, EI will be cancelled here. This will be 384 divided by 48 into 5. 384 divided by 48 into 5, that is equal to 1.6 by 1. 1.6 by 1. So ratio is approximately here, I think some error is there, that is 1.6 is to 1 would be the answer. 1.6 is to 1. So A and B, both the options are matching. And if I want to solve this by Macaulay, that is strain energy approach, if I want to solve this by strain energy approach, so we can solve that by strain energy approach also. Let me do it for this same point load first. Let me do it for point load. So here it is a symmetrical loading condition. This is a both these two loads are symmetric loading conditions. Symmetric loading conditions. This will be directly W by 2 and this will be also directly W by 2. Both will be directly W by 2. Okay, both will be directly W by 2. Right. Next, for the second one, the net load acting on the beam is WL. So this load is going to be WL by 2 and this load is going to be WL by 2. Okay, both the loads will be WL by 2 and WL by 2. Now let me write the strain energy equation for this. So let us take a section here. From the left hand side you want to consider or right hand side you want to consider, it is up to you. Okay, so this will be distance x, this will be distance x. So movement about section xx will be W by 2 times of x, W by 2 times of x. And strain energy formula that is given by U is equal to integral m square dx divided by 2 EI. This is the formula for strain energy due to bending. Strain energy due to bending. How you can get this formula means you can take it as sigma is equal to m by I times of y. This is the formula for bending stress, and strain energy formula is sigma square by 2e times of volume. So now put this equation and do some mathematical operations. You are going to get this result. Okay. So you can refer that. For getting that result, you can refer the derivation in the in some material. Right. It is provided already. So let me focus on this problem. Let me focus on this problem. So now here movement about section xx, this is x equal to 0 location and this is x equal to L by 2 location. This is a b, say it as a, b and c. Whatever due to symmetric loading, I can say that strain energy in segment AB and strain energy in segment BC both will be same. Strain energy in segment AB and strain energy in segment BC both will be same. Okay, due to the symmetric loading, I am drawing this conclusion based on symmetric loading condition. So now the lower limit will be 0 to L by 2 into W by 2 times of x whole square dx divided by 2EI. Right. So total strain energy is what? U is what? U of AB plus U of BC. U of AB plus U of BC. So now that I have to multiply this term with 2 because it is symmetric loading. Now I can rewrite this as W square by 2 square is 4. 2 square is 4, 4 2s are 8. 8 into that is 1 by 8 times of 2 is 4. So W square 4 by W square by 4 EI. And in the denominator, what I will be left with is this is 2 square into 8, 8 into 2 and 2 will be cancelled. This will be x cube by 3. X cube by 3, 0 to L by 2. This will be W square into L cube divided by, this is 3 is already present, so 12 EI into 2 cube, that is x cube, it is x cube, sorry, x cube it is. So 2 cube is 8. So that is W square L cube by 96 EI. W square L cube by 96 EI. This is the strain energy. This is the strain energy. Now, this is the strain energy. Now differentiate this U. Now differentiate this U or dou U by dou W. Partial derivative of strain energy with respect to load. Partial derivative of strain energy with respect to load is going to give you the deflection. That is 2 times of W L cube by 96 EI, which is equal to W L cube by 48 EI. This is equal to W L cube by 48 EI. Okay. Now, if I want to get the deflection of the, if I want to get the deflection for this case, that is for UDL, for the UDL, what I am supposed to do here is that I need to introduce at the midspan, I need to calculate. At the midspan, I need to calculate. So this was the deflection at B, delta at B. Delta, this is equal to delta at B. Okay, so if I want to calculate the same, that is delta, I need to introduce a point load or dummy load. I need to introduce point load or a dummy load at the midspan. Okay, later I will remove this load. So due to the presence of the dummy load, here reaction will be WL by 2 plus capital W by 2. And here the reaction will be plus capital W by 2. Reaction will be capital W by 2. Okay, that is capital W by 2 because I am introducing here dummy load. I am introducing here dummy load. Now, take the section XX here. Take the section XX here. If I want to write the section XX for this, it will be MXX is equal to, that is small w L by 2 plus capital W by 2 times of X. Okay, let me just erase this. Okay, so that is this reaction RA times of X, and this will be small w X square by 2. The moment, the bending moment due to this UDL will be small w X square by 2. Small w X square by 2 here. Right. So now what I can do is, that is M is equal to small w L by 2 time plus w by 2 times of X minus wx square by 2. This will be the bending moment equation. This will be the bending moment equation. Right. Now what I can do here is, that is strain energy is equal to, that is, now put the limits as 0 to L by 2. This is x equal to 0 location, and this is x equal to L by 2 location. This is x equal to 0 location and x equal to L by 2 location. So 0 to L by 2, 0 to L by 2. Now this is going to be WL by 2 times WL by 2 times of into x minus wx square by 2 whole square, and 2 EI is constant, so I'll put this outside. 2 EI is constant, so I will put this outside. Okay, so I need to calculate the deflection. I need to calculate the deflection at the midspan. So what am I do? What am I supposed to do here? Delta B is equal to dou U by dou W. Dou U by dou W. Now differentiate this equation with respect to capital W, or where you are introducing the dummy load. Where you are introducing the dummy load. Differentiate that. And later we have to write in place of W as 0 because W is not present over there. So this will be 1 by 2 EI can be put outside, integral 0 to L by 2. Now differentiate this entire equation. Differentiate this entire equation. This term is constant. This term is also constant. W by 2 is the variable. W by 2 is the variable. So this will be like a form constant plus x, or constant plus x times of some other constant minus, let us say, c1, c2, c3. So I need to differentiate this. I need to differentiate this. So differentiation of this will be what? This constant will be copied as it is, plus x times of this constant c2 minus c3. And after that, again, when you are going to differentiate, this term will be left, right? So this will be multiplied once again, that is x, derivative of x will be 1 into what is the coefficient of x? It is c2, right? So the differentiating this, we will be getting this as wl by 2 times of w by 2 into x minus w square by 2 whole square. This will go down, and this is constant. Okay, differentiation of this will be 0. This will be 0. So coefficient of w is what? 1 by 2. 1 by 2 times of dx. Now do one thing. Eliminate this w by 2 just by saying as keeping w equal to 0. So first you have to differentiate that and write equal to 0, and then you can eliminate. Directly if you eliminate here, then it is not going to give you the result. Directly once you eliminate here, it is not going to give you the result. So this is a strain energy of segment AB only I have written. This is a symmetric loading. So strain energy of segment AB and BC both will be same. So this should be in short multiplied with 2. This should be in short multiplied with 2. And here also I am going to multiply this with 2. Okay, so these two, this 2 and 2 will be cancelled here. And now integrate this 1 by 2 EI times of, that is W by, that is 2 and 2. These 2 will be cancelled here. Both the 2's will be also cancelled here, right? This 2 and this 2 will be cancelled here. So WL by 2, integration of this will be x, integration of x is x square by 2. So WL by 2, I'll pull it out, into x square by 2 over the limits 0 to L by 2, minus integration of this with respect to x is x cube by, this is w by 2 into x cube by 3 over the limits, 0 to L by 2, over the limit 0 to L by 2. So this is equal to what? This is equal to 1 by EI times of, this is 2 square is 4, 4 twos are 8, 8 twos are, so 4, this is 4 and 4, 16. So this will be WL cube by 16. Here it is WL cube by 16 here. And here I think here x will be left. Please be careful here. Here x will be left. So this will be x cube by 3. Sorry. Here there is x cube by 3. It is x cube by 3. Please be careful here. The coefficient of W is x by 2, not 1 by 2. The coefficient of W is x by 2. Because here you should be getting the answer, the value should be WL power 4 should be the multiplier. So this will be x cube by 3. Right, and this will be wx cube by 3, integration will be wx power 4 by 4, x power 4 by 4 here it has to be. Right. So now this will be 3 2s are 6. 6 into that is 2 cube is 8. 6 into 2 cube is 8. That is 48. So this will be equal to WL power 4 by 48 minus WL power 4 divided by, this is 2 4s 8. 8 into that is 2 power 4 is 16. 2 power 4 is 16. So 8 into that is 2 4s are 8. 8 into 2 power 4 is 16. So 16 into 8, that is equal to 128. Equal to 128. Now do this simplification of this. That is 1 by 48 minus 1 by 28 is equal to, this will be 5 by 384. This will be 5 WL power 4 by 384 EI. So this way you can apply strain energy approach. If there is a dummy load present here, dummy load is present. Okay. Now, what if the cantilever beam is carrying a, what if the cantilever beam is carrying a uniformly varying load? So let us do that. Let us do that. What if the beam is carrying uniformly varying load? Say this is W and this is L. Now do one thing here, place this section here, place this section here. So now moment about section XX is equal to, here moment when you are taking, first I need to convert this into force. First I need to convert this into force. That is, force will be half times of base is X, and this height will be, the by taking the similar triangles, that is W by L is equal to, say this height as H by X. So H is equal to WX by L. So this is of the form WX by L into centroid of this, about the section XX. If I am taking, the centroid will be here, which is X by 3 times, which is X by 3 times, right? Which is X by 3 times. So this is of the form WX cube divided by 6L. So this is W by 6L is constant, constant into X power 3, constant into X power 3, right? So deflection here, or first we can also calculate the slope here. Slope is nothing but area divided by area of BMD divided by EI. What is area here? It is, remember here, movement over the section XX should be of the form some constant into x power n only, no other term, plus something times of x, plus some x, x1, x2. If it is coming, then I cannot apply the formula of Spandrel. Please remember that. I cannot apply the formula of Spandrel. So area under BMD will be half or 1 by n plus 1, as discussed, 1 by n plus 1 times of bending moment at this location. It is 0. At this location, it will be, in place of x, just substitute L. Bending moment at this location here, it will be how much? That is W into L cube by 6L, which is equal to WL square by 6. WL square by 6. So the height, the base of the bending moment diagram is L, and the height is WL square, L cube by 6. Okay, so this is WL cube by 6 into base is what? L. Or let me just write in the formula form. Okay, then I'll write it. This is into base into height divided by EI. So this is 1 by n. N is what? 3 plus 1 into base is how much? WL square by 4. Base is L and height is WL square by 6 divided by EI. This is equal to how much? WL power 3 divided by 24 EI. This is the slope. This is the slope. Next, if I want to calculate deflection, what am I left with? I am left with only location of centroid. So centroid here, it will be, that is n plus 1 by n plus 2. N plus 1 by n plus 2. What is n here? Times of L. Times of L. So for deflection, that is area into x bar divided by EI. That is WL cube divided by 24 EI into, what is the value here? What is the value of n? N is 3. 3 plus 1 by 3 plus 2 into L. This is how much? 3 plus 1 is 4. 4 ones, and this is 4, 6, 24. 6 5s are 30. So this will be WL power 4 by 30 EI. That is how you can do for uniformly varying load. Okay. Now, let me take up another typical question in uniformly varying load. Let me take up another question in uniformly varying load so that you will have the clear idea. Okay, if the uniformly varying load is like this, then I'm sorry to say that formula what I have discussed is not applicable here. That is, area and centroid formulae will not be applicable here. Area and centroid formulae will not be applicable here. Now what to do then? See here, let me just give you the logic why it is not applicable. So if I take this section here, this is W and this is L. Whether you take this section on the left hand side or right hand side, that is your choice. So if I take this section here by considering the left hand side or right hand side portion, this is UDL and this is UVL. This is UDL and this is UVL. It is the combination of UDL and UVL. So your bending moment curve for UVL, you have derived it as some constant into x cube, some constant k1 into x cube. And for UDL also, you have derived it as some constant into x square. For UDL, you have derived it as some constant into x square. So this is of the form k1 x square plus k2 x square. I cannot apply the formula of spandrel. I cannot apply the formula of the spandrel here. So what I can do here is I need to, what I can do is, this is the uniformly distributed load. This is the uniformly distributed load. Okay. The result of this load is known to me, that is delta is equal to WL power 4 by 8 EI. From this uniformly distributed load, if I cut uniformly varying load of this type, if I cut uniformly varying load of this fashion, okay, this blue color uniformly varying load, if I cut this, if I cut this area, the leftover load, the leftover load will be something like this. The leftover load will be something like this. The leftover load will be something like this, okay? Which you can transform to this position also. Which you can transform to this position also. Which you can transform to this, okay? Or else you can invert this UVL to this side. After drawing this UDL, what you can do is you can invert this UVL on the other side. Okay, you can invert the UVL on other side. So once you are inverting this, you will get this as the result. You will get this as the result. So here we can make use, we can take the advantage of the standard results. One is the UDL and one is the UVL. These two are the standard loading situation. We can take the advantage of these two. So delta for this one, delta due to UDL is WL power 4 by 8 EI, and delta due to UVL, just now we have derived it as WL power 4 by 30 EI. So delta net will be equal to delta UDL minus delta UVL. Delta UDL minus delta UVL. Okay, just let me just write clearly. Delta net is equal to delta UDL minus delta UVL. This is WL power 4 by 8 EI minus WL power 4 by 30 EI. So 1 by 8 minus 1 by 30 will give us the answer as 11 by 120. That is 11 WL power 4 by 120 EI. So this question can be expected. Okay, this can be another, this is another typical question. So for this question, you cannot follow the regular procedure. You cannot follow the regular procedure. You need to take the advantage of the standard results. You need to take the advantage of the standard results. Guru Vignesh, we can use these superimposition methods when we have the standard results. We will see that, I think not today, tomorrow we will see that.